Hello, everyone. Today, we will continue discussing our topics on bipolar junction transistor. So, in the previous class, let's remind you what we discussed in the previous class. So, in the previous class, we discussed together the load line of the bipolar junction transistor, and we discussed the different modes of operation on the input characteristic, which is IB with VBE, and also the different mode of operation on the output characteristics, and we solved some examples on this point. Today, we will discuss together the transfer or voltage transfer characteristic of a bipolar junction transistor and what are the applications of the BJT. So firstly, we will derive the voltage transfer characteristic of a BJT. Then we will analyze Then we will analyze the performance of a bipolar junction transistor biased through an emitter resistance, and we will also discuss the different applications of a bipolar junction transistor. So let's start firstly with the voltage transfer characteristic. What the meaning of voltage transfer characteristic? So voltage transfer characteristic is a relation between the input volt and output volt. So in our circuit here, as you can see, the input volt is referring to the supply volt here, which is going to be applied mainly to the base to emitter. So V base to emitter will be affected mainly by the input volt. And the output volt is nothing but the V collector to emitter. So V collector to emitter is representing the output volt. The characteristic we can see here is called the static characteristic of the NPN transistor. Let's discuss it together, guys, to see what the meaning of these characteristics here and what's happening exactly. So we mentioned previously, guys, that during the input volt here, less than the base to emitter, you know that we mentioned we have N, P, N layers. So this is collector, base, and emitter. So for the base to emitter, in order to allow a current to flow between the PN junction, so VBE has to be greater than the turn-on voltage of the diode, which is 0.7 volt. For instance, for sure it's according to the data sheet, but let's say in general, for the general purpose diode is going to be 0.7 volt. So if the volt is greater than 0.7 volt, we expect that this junction will act as a diode and the current will start to flow. And if it is less than 0.7, so this means you have nothing happen. So we can say that if the volt is the input volt, which is V input here, if the volt is less than 0.7, because if this is less than 0.7, for sure the volt here will be less than 0.7. So in this case, we expect that the transistor will be off. So I can say that if the transistor is off, so this means the current here is 0, and this is for I base, and the same is also for I collector will be 0. So if I collector is 0, so the output volt is going to be the same as V plus. So I can say that this is going to be V plus if the voltage here, the input volt, is less than VBE on. Okay, so if the volt, the input volt is less than VBE on, V base to emitter on, so 100% the transistor will be off. So this is the cutoff region, and the output volt is going to be the same as the volt of our supply here because the current equals 0. So this is the first part of the operation. Then, if the volt is greater than 0.7 or the turn on volt, so we expect that a current will start flowing here. So IB will not be 0 anymore. And if IB is not 0, so this means we will be in the active mode, and I collector equals beta times I base. And based on that, you can have a relation now between V out and V input. And we will drive this relation now in our examples. And we will find that this relation represents this straight line. Okay, so this part is going to be valid for the active mode. And you know that we mentioned before the active mode, this relation I collector equals beta I base is valid until the stream or the out of stream mode, which is when the I collector is increased too much and the voltage drop across the resistance RC is very close to the V output, V plus here. And in this case, this means the I became maximum and the transistor will be saturated. And saturated means our volt of collector to emitter ideally became 0, or practically it's around 0.2, which is the saturation mode. So in this case, we can say at a certain value of volt of VBE, the value of V collector to emitter will be the VCE saturation. And at this point, we can say that the transistor is working in the saturation region, which is the linear region, okay, according to our characteristics. So let me draw the characteristic here between I collector and V collector to emitter. So if this is our characteristic like that, so the active mode is in this region, the cutoff is here. So this line here represents the cutoff. And at a value less than VCE saturation, which is 0.2, this will be the saturation region. And other than that, all of this region represent the active region. Okay, so this is the relation what we have now for the output and input volt, and we call it static voltage voltage transfer characteristic. Let's apply that to the NPN transistor on a certain common emitter circuit and see the performance and see the characteristic in this case. So in the circuit, you can see here, guys, we have a common emitter, a common emitter transistor, BJT. The collector is connected to a resistance of 5 kilo ohm and a 5 volt supply. And the base is connected to a resistor of 150 kilo ohm, and the input will be applied here. And then the emitter is connected to ground. And we have, in this case, we will assume that the transistor parameters VBE on is 0.7 volt, the beta is 120 of this transistor, and the VCE saturation is 0.2 volt. What we need to do here is we need to develop the voltage transfer curve of this circuit. So we need to apply now different value for V input and observe the output volt here, which is V collector to emitter. So let's start firstly, guys, from a very small value. So we can say that if the input volt is less than 0.7, so from V input greater than 0 and less than 0.7, so 100% since the VBE on equals 0.7 volt, so if this is less than 0.7, 100% no current will flow in this direction. And the internal junction of the transistor will be reverse biased. So no current will flow. Okay, nice. So in this case, we can say that the transistor is in the cutoff mode. And the collector current and the base current will be 0. Let's continue, make all of the values of input volt, and then draw our curve after getting all the numbers. Now, if we increase the input volt more than 0.7, let's see what will happen. So once the voltage is greater than 0.7, so expect that the base current will start flow. And in this case, we expect to have a collector current and emitter current. So starting the analysis from the base current, so we can say that I base equals V input, which is going to be greater than 0.7, minus 0.7 divided R base. Then we can say now the collector current equals beta times I base. So let's substitute with this relation right here. So it's going to be beta times V input minus 0.7 divided R base. So this is the I collector. And if you would like to get a relation for the output volt, which is VCE, so we can get it from the loop here outside. So from this relation, we can say 5 volt equals ICRC plus VCE or V out. So we can say now V out, which is VCE, V collector to emitter, equals 5 volt minus IC times RC. And let's substitute now with the IC relation we got here. So in this case, the output volt will be 5 minus beta times V input minus 0.7 times R collector divided R base. So this is nothing but a straight line equation, approximately a straight line equation, guys. Okay, and as you can see, with increasing V input, this term will be in negative sign, so we expect to have negative slope for this part of the curve until having the saturation of our transistor at V collector to emitter saturation. So the I collector will continue increasing until reaching to the collector to emitter saturation. So this is the voltage transfer characteristic. So we can draw now the voltage transfer characteristic and write the numbers. So if you substitute with the number here right now, so you will find that the value of VCE to reach to saturation is at V input equal 1.9. So how can you do that? So here in this relation, guys, you can make this relation equals to 0.2 volt, which is VCE saturation, and find the corresponding input volt. Okay, so here in this relation, in order to get the value of V input at the collector to emitter voltage at saturation, so we can say 5 minus beta, which is 120, times V input minus 0.7 times R collector, which is 5K, divide R base, which is 150K. So this value here should be the same as V out. And I would like to get the boundary at the V collector to emitter saturation. So I can say this is 0.2 volt. Here you will have just one unknown in this equation. And if you get this V input, it will be this value right here, which is 1.9 volt. So we can draw this curve now and write down the numbers. So the value here is corresponding to the 0.2 V collector to emitter. The value here is the turn on volt, and this value here can be the volt of V plus, because the current here is 0 and the transistor is in the cut-off mode. So this is the boundary of the voltage transfer characteristic of this transistor. So this means, guys, you can have any operating point on this curve here in active mode. So the advantage of knowing the voltage transfer characteristic is to identify the operating mode and what the relation between Vin and Vout in our circuit. Okay, this is for the NPN transistor. What about the PNP transistor? So let's see together, in case of PNP transistor, what will be the case. So here is another example. So consider the same technique to obtain the voltage transfer characteristic. So VTC stands for voltage transfer characteristic. So find the voltage transfer characteristic for a PNP bipolar junction transistor where VEP on is 0.7, the same turn on volt, and VEC saturation is 0.2 and beta is 80. So here is our emitter. This is the collector, sorry, emitter to collector, and this is this represents VO terminal, and here our collector to the collector terminal to ground, and here we have the V input, which is the is a function of the VBE. So by the same way, guys, we are gonna follow the same procedure. So for PNP transistor, guys, if the voltage input here is from 4.3 to 5 volt, or let's say from V plus minus VT on to V plus, so this number is nothing but V plus minus V E B on. So from 4.3 to 5 volt, the transistor will be in the cutoff mode. So in this case, we can expect that the I base and I collector will be 0. And in this case, guys, since you have 0 current here and 0 current here, so the volt here will be the same as the ground volt, which is 0. So we expect that Vout will be 0 in this case. So the output voltage then is 0. And for any volt less than 4.3 volt, this transistor will be on and will be in forward active mode. So we can apply our relation now, which is I base. So we can get the base current if the volt is less than 4.3. So we can say now I base equals 5 volt minus the turn on volt, which is 0.7, minus V input divide the R base, which is 200K in our case. So this is I base. Now we can get the I collector as a function of I base by multiplying times beta. And by the same way, we can get Vout. So Vout, in this case, we can get it from the Kirchhoff, applying Kirchhoff here in this branch. So we can say that 5 minus the or Vout equals I collectors times RC. So we got already IC from the relation here. So we will just multiply this times the collector resistance here. So we don't need to make Kirchhoffs. We just need the volt across this one, and we got the current. So it's going to be just RC times this current. So this is the equation, guys. And again, this equation represents or can be represented by a straight line equation. Until which point? Again, until the saturation of our transistor. So the saturation of our transistor here, guys, is going to be at Vout equals 4.8. So if V out equals 4.8, so this means our V emitter to collector equals, or V emitter to collector saturation equals 0.2. So in this case, if this is 5 volt, this is 0.2. So the volt here across the resistor, which is V out, should be 4.8. So how to get the value of Vn corresponding to the 4.8? You just need to substitute in the relation. So you have here IC times RC plus 0.2 equals 5. So you can get the value of IC, and from that you can substitute and get the value of the input. Okay, so this is, guys, how can we get the voltage transfer characteristic in our case. Again, I'm gonna repeat again, how can we get the value of 2.8 here? So this value, if we go back here, guys, so at saturation, VEC sat equals 0.2. So we can say now 5 volt equals IC RC plus VEC on. So from here you can get the I collector, and then substitute from I collector in the relation here in order to get your input. Or by another way, you know already the value of 4.8. So we said that 4.8 is our volt at saturation. So make this equation equals 4.8. So you will have just one unknown, which is V1, and you can get this. I think this is easier. So let's keep this one here. So you don't need to substitute here again. Just use your relation. Okay, guys. Okay. So this is how can we get the value of Vn, which is corresponding to the saturation. Okay. So this is now the voltage transfer characteristic of the PNP transistor. Now, let's do that in simulation, guys, and see the performance. I will make this simulation with you, and we can see the results. And let's see how can we do this simulation. So this is our example here. I'm going to do that on a transistor with this part number 2N3904. So this is NPN transistor. So what we can do now, I'm going to represent the same circuit here with the same numbers we already solved it in our example. So let me go to PSpice. So this is our PSpice. And here you can see we have V input or V1. It's written 0 VDC, but this is going to be DC sweep. So don't care about the 0 volt right now here. We have V plus equals 5 volt. This is our collector 5 ohms. This is our transistor 2N3904. And this is the PSpice 1. And this is 150K, the base resistor. What I'm going to do is go to the simulation editor and select the DC sweep. And in the DC sweep, I will select the voltage source, which is the input volt, V1. And I will change V1 from 0 volt to as big as I can. So if you have a look to our example here, so the values we could see in the transistor here, we need to have a value greater than 1.9. So I'm going to move it from 0 to 6 volt, for instance. So I'm going to change the supply input volt, V1, from 0 to 6 volt and see the performance. So here again, I changed that from 0 to 6 volt with a step or increment volt of 0.05 volt. and then press OK. I added here a voltmeter, and this output volt should appear with our variable, which is going to be V1 when we run this simulation. So here is our characteristics. So as you can see, guys, firstly, you can observe that the relation is not completely a straight line equation. This is normal, but we will assume the linearity of our relation all of the time. Okay, guys, so you have an E curve here. It's not like a broken curve as we have in our assumptions. Okay, so again, the volt at the smaller values of the input, less than even it's not 0.7 exactly here. So this depends on how much V turn on in our transistor in the data sheet. So here it started decreasing actually from like 0.6. So here is 0.7 exactly. So this is our first part. And then we have the active modes until the volt is reached to the saturation. So the saturation happened here at this value of volt, which is around 0.2, as we mentioned. And the volt here actually is not exactly as we have also in the calculations. So it depends, guys, on the transistor number itself. So the transistor itself is not the isn't having the same numbers as we mentioned, like 0.7 or 0.2 exactly for our transistor. So for that, you have different mini curves for this transistor right here. Okay, so this is the simulation showing the voltage transfer characteristic of this NPN transistor. Okay. So as you can see here, guys, we have our numbers on this simulation right here. Now, we need to see the performance of our transistor, but with emitter biased resistor. So instead of having our emitter connected to ground, I will add a resistor to the emitter, then connecting this emitter to a negative volt, as you can see right here. So what is the performance or DC analysis, or how can we make the DC analysis in this case? So simply, guys, we can start firstly from the base, like what we made also in the common emitter. So we can write the loop of this part. So we can say this volt equals I base times this resistor plus VBE on plus I emitter times times emitter resistor plus V minus, which is minus 1.8. So this is the first loop. If we write that down together, so VBB equals IBRB plus V base to emitter on, which is 0.7 as given here, plus I emitter R emitter, which is 3 kilo ohms, plus V minus, which is minus 1.8. And now you know that I collector equals beta I base, and I emitter equals 1 plus beta times I base. So you can replace I emitter in this equation by this relation. So it will be a function of I base. So in this relation now, guys, VBB is given, R base is given, VBE on is given, R emitter is given, V minus is given. So the only unknown we have in this relation is going to be the base current. So if you do that, you will get the value of I base. So here is the solution of I base. Once we get I base, so we can now calculate the I collector and I emitter. So you know that I collector equals beta I base in the forward active mode. So I collector will be beta times I base. We have beta equals 75. So we can substitute in the relation and get the value of I collector and substitute again in the IE equals 1 plus beta IB to get the emitter current. So we got now the three emitter currents. Once you got all the all the three currents, whatever analysis you need to do, you can obtain. We need to get the collector to emitter volt. So simply apply a Kirchhoff loop here on the output side. So we can say V plus minus V minus equals I collectors times R collector plus VCE plus I emitters times R emitter. We got all of the currents, so you will have only one unknown, which is V collector to emitter. Or you can say V collector to emitter equals V plus minus V minus minus the currents times the resistors. So V plus minus I collector R collector minus I emitter R emitter minus V negative. So V plus is 1.8. The collector current is 0.2. The resistor is 7K, 0.2 milli times 7K. Then 0.203 emitter current times 3K minus the negative volt, which is minus 1.8. So this will provide us with the value of VCE. Again, don't forget, after you finish the calculations, if the value of VCE is greater than VCE saturation, so this means you are correct in the active mode. So our assumption in the active mode is correct. If the value is negative, so this means our assumption is incorrect and the relation I collector equals beta I base is not valid, and we are working in the saturation region. And in this case, the value of VCE will be 0.2 volt. Okay. After understanding, guys, the different modes of operation of our transistor, let's see together the different applications. So the first application is the use of transistor as a switch. And it's mainly going to be power switch. So it can be for small current and high current as well. So you can find some BJT with high currents. The one we already used in our lab, or sorry, we will use it in our lab. It's going to be a relatively small current. However, we have some other BJTs with high value of current. I can share some data sheet with you for this power BJT. So let's see the application as a switch. So in this circuit, guys, here, if I could connect a voltage source, so this voltage source can be small or can be high. So it can be our AC supply at home, domestic loads, like for instance, 110 or 120 volt, okay? And it can be DC for sure, it can be AC, but you have to know that the transistor is unidirectional current flow, so it will not allow the current to flow in the negative direction. So it will allow the current to flow only in one way, in the positive half cycle of the AC supply. So we have VCC here and we have a certain load. So this VCC, for instance, can be applied to a DC motor. So this DC motor can be like 200 volt or more, okay? So this is valid to be also for power application. So this is here our DC load in this case, and this terminal represents the collector, and this is our emitter, and here is our base. So when you apply a voltage V1 here to turn on this transistor in the saturation mode. So you will allow a current to flow and you will have your load supplied. And if you apply volt less than 0.7, so this means your transistor is going to be turned off and you will have 0 volt right here. You can make this, guys, on PSpice to check it, for instance, with these numbers. So if you use just 5 volt, a resistor of 100 ohm, and connect that to a LED and use our transistor and apply here, one time apply 0 volt and another time apply 5 volt and see what will happen to the LED. So you will find that at 0 volt, you have 0 current flow and the LED will be turned off. And if you have 5 volt, you will have a current and the LED will be turned on. So the resistor here is nothing but a limiting resistor in order to avoid burning this LED, because by the end, when the LED is turned on, it will be a diode. And you know the turn on volt of a diode is around 0.7 volts. So you have to dissipate some power or make a voltage drop across this resistance to avoid burning the diode to limit the current. Okay, so this is here one of the applications. So you can use the BJT as a switch. It can be small current and can be high current, as we mentioned. So it can be, for instance, applied for our circuit we are doing now, the 4-quadrant operation of a DC motor. So you can apply it for a DC motor as well. But for a DC motor, you need 4-quadrant, which means you need 4 transistors like that. So the modes of operation, we have the first mode, which is if input A and input B, so both of sides here are active low. So this means the output A and output B will be 1, which means stopping. So active low or active high in this case is referring to the lower switch or upper switch. Okay, so lower switch or upper switch. So you have the 4-quadrant again. You can apply the transistor to work through this transistor and that transistor, and this will allow a current to flow in this direction, and this is forward. If you reverse in this direction, so the current will flow in the opposite direction, and you can for sure make the other 2-quadrant operations. So this is, guys, the application in DC motors. Take care that if you will apply such circuits, you have to have a driver to avoid having a short circuit in your power circuit. You know that the signal or pulses will be applied between base and emitter. So the emitter should be connected to ground. In the transistor here, guys, you can see that the transistors are reversed. So it's not the same direction, which means this is PNP transistor and this is NPN transistor. What is the advantage of using PNP and PN and NPN? The advantage is you can have a common pulse. You can have a common pulse. So in this case, this is an advantage, and you can avoid having what's called DC to DC isolation in order to provide the pulses. So this is one of the technologies or one of the circuit topologies we use in order to avoid having a short circuit in our design or in our power circuit. Okay, so using both PNP and NPN transistors. Okay. Another application, guys, like what we had in MOSFET, we can use the transistors also for the digital logic. And the same, this is going to be also in cutoff and in the saturation region. Okay. For instance, the circuit we have here is representing NOR logic. So if this input is 0, so we have 0 current. So 0 current here, and the volt of this point will be 5 volt. So 0 provide here 5 volt. And the same as well for the other transistor. So if 0, 0, this means you have V is 5 volt. If one of them is on, one of these transistors is on, so this means and on and in the saturation as well. So in this case, you will have this volt here equals 0.2, which is representing active low. So 0.2 can be represented as active low. And if you have both in the saturation, so still you have active low. So this is, guys, the idea of having digital logic from the BJT in this circuit. And again, you can make a lot of digital logic circuits by reconfigure the two transistors in the circuit. A third application, guys, is the amplifier application. We just made the last lab yesterday using the common source amplifier for MOSFET. So you can do also amplifier using BJT. So the amplifier is going to be in the active mode region. So once you have a certain operating point in the active mode region, so this is the voltage transfer characteristic we just discussed today. So Vn is going to be the base to emitter volt side, and V out is going to be the collector to emitter voltage side. So you make the DC biasing and make the DC analysis to identify the operating point. And after that, you can add an AC signal. So as you can see here, guys, we have the VBB here, which is the DC biasing for our transistor to provide a certain DC base. And then you will have the AC signal, which is going to be amplified. So if this is, for instance, the delta V input, so this is the input side. So if this is delta V input from this peak to that peak, so every peak will be reflected on the voltage transfer characteristic, and the output in this case will be like that. So this is the amplification application of our BJT. So it can be used also as amplifier in the active mode. So a summary, guys, for what we have discussed today. So we discussed the voltage transfer characteristic of a bipolar junction transistor. We discussed the NPN and PNP, and we drive together how to get the voltage transfer characteristic from both of types. Also, we made the DC analysis if we have emitter resistance connected, and the emitter resistance also is biased from a negative supply volt. So the analysis is going to be the same. So we apply the same relation of the active mode, I collector equals beta I base, and the difference will be only in the topology in terms of the circuit analysis. So if you have just a resistance, so your loops or Kirchhoff equation is going to be a bit different compared to the common emitter type. And by the end, we discussed the different applications of our BJT. Next class, we will go more in deep in the DC analysis, and we will discuss the cascaded operation of a BJT. Thank you, guys, and have a nice evening.